So as we look to finish off this unit, we're going to turn to the inverse of relation, which in some ways is not a transformation, but in a lot of ways it is. We won't be treating it as a transformation, we'll be treating it slightly differently, but in my experience I found it's easier to treat it as though it's something different than to try to combine transformations to make the inverse. So any relation is actually just a set of ordered pairs. Normally, if we're talking about graphs, we call them points, but they are ordered pairs, they're x, y. So if we have a relation R, the inverse of it would be, it looks like it's R to the power of -1. It's not actually an exponent, it's a symbol that means inverse. What it means is that if we have an ordered pair of AB in the relation, then to get the ordered pair that belongs to the inverse, we just flip around the A and the B, and we turn it to BA. Literally, the easiest way to think about this would be to switch the X and Y of the points, and that is what will be. So the inverse of this, we have the curly bracket for a set of points. First point 2, 8 will flip into 8, 2. Second point 1, 1 will flip, even though it won't look like it flips, it does, into 1, 1. Next point flips to -64, -4. Last point flips to -1000, -10. What matters is that the X and Y flip, not the negatives. These do not change signs at all. If we're graphing, we still need to look at the coordinates of the points in order to figure out what the inverse is going to be. So I'm just going to list off these points in A in order. So that first point is at -6. Actually, I'm going to do that in blue to match the graph that's there. Is at -6, 4. The next point's at -4, 6. 0, 6. 2, 2. 4, 2. And 6, 0. I'm also going to list out the points that will be on the inverse. It's the same method as before, flip the X and Y. So the first point will turn into 4, -6. Next one would be 6, -4. Then 6, 0. 2, 2. 2, 4. And 0, 6. To get the graph, we'll just graph these points out. I'll have to go a little bit beyond what's there. So 4, -6 would be about here. 6, -4 about there. 6, 0, that's easy. 2, 2. 2, 4. And 0, 6. Now, I went with the original graph. I took those points from left to right. It won't necessarily be like that on the inverse, but I'm just going to connect those points in the same order that I graphed them. We're not going to go across anything. And this, if you're looking at it and trying to figure out how the relation is to the original, this is actually a reflection, but about a different line. It's not a y-axis or a horizontal reflection. It's not an x-axis or a vertical reflection. It's a reflection about the line y equals x. So if you imagine that line as the mirror, it flips on that line. It's difficult to view that as a reflection, which is why I avoid talking about it as a reflection. but it can be viewed that way. Moving on to B, we've got a parabola with an equation there. We still need to look at the points on the graph. I'm just going to pick 3 of them, because what we know about inverses is that the shape will stay the same because it is just a reflection. It will just be in a different orientation. So now that I know that, I can take these 3 points, determine the inverse, and then come up with the new graph. So the first point is at -1, 0, then a point at 0, -1, and the last point is at 1, 0. Determine the inverse of those points. The x and y flip, so we get 0, -1, -1, 0, and 0, 1. So we will have some points go on top of each other. That's okay. The first one at 0, -1 goes here. -1, 0 goes here. And 0, 1 goes there. For the shape of this, it's still a parabola, but now it's reflected, so instead of opening up, it's actually opening to the right. Again, this is a reflection. This would be the line of reflection, and it's very difficult to see, at least in my mind, that is a reflection, so that's why we'll just go with switching the points. In a lot of ways, that's easier to determine the inverse. Moving on, I could give you an equation and ask you to find the inverse of an equation. The method is going to be different because we're not dealing with points on the graph, but the overall thought process is the same. With points, we switched x and y. With equations, we also switch x and y. So in this equation, y becomes x, and x becomes y. Nothing else, nothing more. We just do that. And then we have to get y by itself. So on the right side there, I'm going to subtract 6. So we get x minus 6 equals 3y. Divide everything by 3. Simplifying what I can, x over 3 does not simplify. Minus 6 over 3 does, that becomes 2. And that equals y. That is the inverse function, the inverse equation of what I gave you. Same idea here with b. X becomes y and y becomes x. We need to back this up and get y by itself, so I'll add 4 to both sides. We end up with x plus 4 equals y squared. To cancel off that exponent of 2, we'll need to square root both sides. And don't forget, this is something that may have got lost along the way since pre-calc 20, is when you take the square root and you do that operation yourself, we need to have a plus or minus on that new square root. So left side, there's really no simplifying we can do. We just have the plus or minus square root of x plus 4 equals y. That is it. That is all. Now, something that has been talked about a little bit in Foundations Pre-Calc 10 and then occasionally in Pre-Calc 20 is the idea of whether or not something is a function. So every equation, every set of ordered pairs, every graph I have given you so far has been the graph of a function. That is no guarantee that the inverse is a function. The inverse might be and it might not be. But I will ask you to tell me if the inverse is a function. Specifically on graphs for now, but once we hit Calculus 30, there will be more discussions on whether or not something is a function and how that affects the math later on. The method to determine if something is a function is called the horizontal line test. And if the original function passes the horizontal line test, then because of the way that the inverse is graphed, it's a reflection on the line y equals x, then the inverse function will pass the vertical line test. And this is what was talked about back in Foundations Pre-Calc 10. So if the original passes the horizontal line test, which I'll explain what that is in a second, then the inverse passes the vertical line test. So the vertical line test you did back in Foundations Pre-Calc 10, which said if you can draw a vertical line through a graph and it passes through only once, then that graph is a function. The horizontal line test was a test that's designed to tell whether the function is one-to-one or many-to-one, something that'll be talked about more in calculus. We're going to adapt that here. So if I can draw horizontal lines through the original, and those horizontal lines only pass through the graph one time, maximum, then the inverse will be a function. So, taking a look at these, in A, I can draw this horizontal line here. That horizontal line passes only once. If that were the extent of the graph, it would pass the horizontal line test. I can draw a horizontal line here and it passes through the graph never, which is also a pass. But as soon as I find any horizontal line that passes through the graph more than once, then it fails the horizontal line test, and therefore the inverse would not be a function. So in A, because of that line, and also could have called it this line or this line, it doesn't matter which one, as long as you can find one line where it fails, the inverse is not a function in A. B, I can draw as many horizontal lines as I want through that graph, and every single one of them passes only once, or if I go above or below, passes through no times. I cannot find a horizontal line that passes more than once, so because of that, it passes the horizontal line test, which means that the inverse is a function. C, I have many different options for a fail of the horizontal line test, and as soon as it fails any line, then the inverse is not a function.